Good afternoon, and now we will be deriving expressions for those derivatives which are, last class remember, dfx by du by u1 or dfax by d alpha, etc., which are u derivative, alpha derivative, q derivatives like that, and we understand that these derivatives are evaluated at steady state. It's a very important thing. And second thing, we should understand that we are using stability axis system, right? And by now you know what is a stability axis system. To revise your understanding, we know that if this is the plane which was having x-axis like this, z-axis like this, and it was having a steady state angle of attack, let's say alpha 1. So it's cruising at an alpha 2 degree, so I'm saying alpha 1. When I'm defining stability axis system, I'm saying I'm aligning this x-axis along the total velocity in the vertical plane, and I'm calling it xs, and naturally your z will become zs. So you could see that now I am not working in x and z axis, I'm instead working on xs and zs, and the consequence of that is W1 becomes 0, right? Because there won't be any component along W1 when I'm talking about a vertical motion restricted to vertical plane. And since it's very simple that this is the airplane, this is the velocity vector, and if this is the x-axis, I align with the x-axis. This is stability axis. Now there cannot be a component perpendicular to xs. So z component along zs will be 0, so W1 is 0. So we define stability axis at steady state. We confine our or redefine our axis system aligning with the velocity vector in the vertical plane, so that your W1 is 0. And we have to evaluate these derivatives keeping those things in mind. So if I draw this diagram for more clarity, you could see that this is alpha 1, this is the x, what I was showing here, and this is the perturbed u, this is the steady state value u1, because that is the xs direction. And now because of disturbance, total velocity direction will change, which is given here. Let's say v star. Okay, whole total dynamic pressure will be now, if you see, ideally speaking, total dynamic pressure will be half rho u1 plus u square plus v square plus w square, half rho u square, right? That is, u square is resultant of total velocity having perturbed quantity u, v and w. And since at steady state there were no v1 component, no w1 component, so in general form I can write it like this. Okay. Now I want to find out these derivatives. Let's say I am trying to find out dfax by du by u1. Let us see how it can be done. I can write fax is equal to cx into q bar s. Similarly, I can write faz equal to cz to q bar s. I can write aerodynamic moment as cm q bar s c bar. Clear? There is no problem. I'm just using the definition of fx, faz and ma through the definition of cx, cz and cm as we did for cl, cd and cm, right? Now we want to find out dfax by du by u1. Let us see how would we handle this. So let me go like this. Fax is equal to cx into q bar s. So d, this is very mechanical, so follow my steps. U by u1 will be equal to d cx du by u1 into q bar s plus Cx into S dq bar by du by u1. No issues, class 11th, 12th. What next? Let us see what is dq bar by du1. dq bar by du by u1. What is it? Let us check this. You know what is q bar? Q bar we have already understood. It is half rho u1 plus u whole square plus v square plus w square, half rho total v square. What is the important thing you should remember? That this to be evaluated at steady state. So all these things to be evaluated at steady state. So dq bar by du by u1 has to be also evaluated at steady state. So if I write dq bar by du by u1, I will write it as u1, which is constant, dq bar by du, and I can differentiate this and put a condition that at steady state all the u, v, w are 0, isn't it? At steady state u, v, w all are 0. So I will take the differentiation with respect to u. So this will give me u1 into rho u1 plus u at steady state, and that will be nothing but rho u1 square. So what did I get? I get dq bar by du by u1 is nothing but rho u1 square. As simple as that. Okay. So if I want to write dfAx by du by u1, what will be my result? I have to change this term because we have evaluated this by this term. First step. Right. So I can write dfAx by du by u1 is equal to dcx by du by u1 into q1s. Now I write 1 because I have to evaluate this at steady state. So for q I write q1s plus cx s into rho u1 square. Now the question comes, can I find an expression for dcx by du by u1? That is the question. And then also, since I am evaluating at steady state, what is the cx? Cx is what? Cx is a component which is coming because of drag, lift, etc. All the forces resolved along the x direction. But once I say evaluate at steady state mean at a condition 1, so I write the cx has to be at a condition 1. Right? So cx is evaluated at steady state. That is the understanding. Right? What is cx1? Let's see like this. Suppose this was x and the velocity was in this direction, then CD would have been like this. Cx is defined like this in this direction. If the flight was like this, the condition was like this, what would have been the Cx1? Cx1 would be nothing but minus CD or CD1. Right? Now let us see in a generic sense of understanding, how do I find out what is Cx1 in terms of CL and CD. Please understand, we are trying to find out everything on CL and CD because we are using stability access system, right? That is what I was mentioning in the beginning also. So let us see what happens. You know the Cx for small angle, I can write it as CD plus CL into alpha. You can use this Cx, CL is here, CD is here, alpha is there. So you can easily find out how do I define Cx and CD. So this is your alpha, put the geometry and you can find this. So at steady state, the alpha here which is perturbed alpha, right? Perturbed alpha, that means perturbed alpha at steady state is 0, so this gives Cx1 is minus CD1. You get the same answer as we could see from simple understanding. If you see my last course lecture, I have developed this equation assuming this sort of an understanding. But in this course, I'm trying to go a little bit more evolved way so that you understand the basic mathematics or basic algebra or basic techniques. Not even, I don't call it algebra or a mathematics. It's how to manipulate the expression, how to camouflage physical understanding into the expression to make life simpler. Okay? So this is Cx1 is handled. We know this. Now, next question comes, what is dCx by du by u1? Let us see that. We again start with this expression, Cx is minus Cd plus Cl alpha. Please understand, once I have written this, I have assumed that alpha, the perturbed quantity, is very small. That is why you know that there will be a cos alpha term, the sin alpha term, sin alpha becomes alpha, cos alpha becomes 1. So we are again using the advantage of small perturbations. So if Cx is this, what is our aim? Our aim is to find dCx by du by u1. So now we write dCx by du by u1 is equal to minus dCd by du by u1 plus dCl by du by u1 into alpha. Right? But what is that we cannot afford to forget? That this derivative has to be evaluated at steady state. And to be evaluated at steady state means what? As far as this expression is concerned, because I know alpha is perturbed alpha. But at steady state, what is the value of perturbed alpha? It is 0. At steady state, alpha, which is a perturbed alpha, is 0. So dCx by du by u1 is minus dCd by du by u1, and that is also sometimes written as CDU. Okay? We'll try to give an understanding of what is this CDU means. But as far as expression is concerned, now I know that dfx by du1 I can easily write as dfax by du by u1 I can write as minus cdu plus 2cd1 into q1s. Is it okay? You should not get surprised where from this two term came. Please see that this is rho u1 square. So we have taken a common with q1. So this rho u1 square has been written as half into rho u1 square into 2. And this is q bar, q1 bar. That has been taken here. So that is how you got this term 2. Okay? It's a simple manipulation you should be able to do. So we have seen primarily that this derivative can be evaluated if I know what is the value of CD1. What is the value of CD1 means what? What is CD? CD is, you know, for an aircraft, CD is CD naught plus KCL square. Let's say I'm talking about a low subsonic airplane. So what is CD1? CD1 is the value of CD. CD1 is the value of CD at steady state. What is our steady state being considered here is a cruise. So at cruise, question is what was CD naught value and what are the value of CL1 with which it was cruising. Right? For example, if it was cruising at a minimum thrust required condition, then you know that CD naught equal to KCL square, and you can easily know CL1 is nothing but under root CD naught by K. That is the cruise condition. That is the condition at steady state for our case. And what is CDU then? The question comes, what is CDU? Let us see, what is CDU? CDU, I can write it as dCd by du by u1 by definition, and I can write this as u1 by a into dCd by du by a. What is a here? Anybody's guess? U is the velocity of sound at that altitude. And what is u1 by a? It becomes the Mach number at steady state. So it becomes m1 into dCd by dm. Now you see very interesting phenomena. The CDU is immediately giving us some sort of a very, very significant understanding. If you recall, CD versus Mach number for an aircraft, something looks like something like this, right? Typically, this is a transonic zone, maybe 1.1, 0.98, or to 1.1 or 1.2, depending upon the configuration. Now you could see if you are in this region, here dCd by or dCd by dm is greater than 0, whereas here dCd by dm is less than 0. So depending upon what is your flight regime, this dfx by du1 will change depending upon the value of CDU. Sometimes it becomes positive if it is subsonic type, it becomes negative if it is supersonic. So this plays an important role. Okay? You will see why I am stressing this. Overall stability, overall dynamic stability, when you are going to study, we have agreed that we will study the response of U, alpha, Q perturbed quantities. To know U, alpha, Q, we need to solve perturbed equation of motion, and to solve perturbed equation of motion, we need to know the values of fx, fz, and m, and fx, fz, and m depends upon the U derivative. So depending upon subsonic or supersonic, the responses will change, and it may affect the dynamic stability character of the airplane. So it is extremely important to understand this in a real physical sense. Okay? So we have understood what is dfx by du by u1. Now let us go to the next. We are continuing with u derivative, or you say u by u1 derivative. We have finished dfax by du by u1. Now we want to do something with fz by du by u1. And the method is similar to what we have done. So let us write faz as cz q bar s, that is where from we started, and we have to find this derivative. So df az by du by u1 will be equal to d cz by du by u1 q bar s plus cz s dq bar by du by u1. By now you should be able to do yourself actually, right? Now let us see from the earlier diagram, you can write cz is minus cl cos alpha minus cd sin alpha, right? And if I apply small angle approximations, this becomes cd into alpha, because sin alpha equal to alpha and cos alpha is 1 for small angle approximation. After all, we are using small perturbation theory, and alpha is a perturbed quantity. Okay? Now, if that is true, then I can write at steady state cz1 by the definition of steady state and the notation we are using. So this will become minus cl1 minus cd into 0, because alpha perturbed is 0 at steady state. So what finally we get is cz1 is minus cl1. This is one we have got. Second thing, now we do dcz by du by u1, which is this term we are trying to evaluate. Please remember, we have to evaluate at steady state. Do not forget one thing, already we know how to handle this term, dq by du by u1. So let us see this is dcz by du by u1, and that I can write as, from that expression I use this. So let me write this here for your comfort. Cz is minus Cl minus Cd into alpha. So dcz by du by u1 I can write as minus dCl by du by u1 minus dCd by du by u1 into alpha. Right? Now you know that this has to be evaluated at steady state. So what happens? At steady state means alpha goes to 0. So what you are getting? You are getting dCz by du by u1, which is also known as, can be denoted as Czu, which is nothing but minus Clu. So simple. So you know what is this term, nothing minus Clu. We know what is this Cz1 is nothing but Cl1. So if I want to calculate, or if I want to derive the expression for dFaz by du by u1 at steady state, I get dCz by du by u1, which we have seen, minus Clu into Q1s, right? Plus for Cz, we put minus Cl1. What is our aim? Our aim is to find out this expression. You know, dFaz by du by u1 evaluated at steady state is dCz by du1 evaluated at steady state is minus Clu, then Q1 bar s plus Cz is minus Cl1 s, and dq by du1 already we have seen, we have derived it as rho u1 square. Right? So if I now take Q1 as common, so I get, this is, I write it like this, minus Q1s Clu plus 2 Cl1. That is what is this expression. Again, you should understand where from this term 2 came, because it is here. This was Cl1 into S rho u1 square. So what we have done, we have written as Cl1 into 2 into half rho u1 square S, and for this we have put q bar. So that 2 is here. Clear? No issues? So we have got these two terms, dFaz by du by u1. We have also got term dFax by du by u1. Here, what is Cl1? Cl1 is the Cl at steady state. Let's say, what is our steady state? It is a cruise. So what about the cruise Cl? That is Cl1. What is Clu? Let us understand that. This is dCl by du by u1. As we did for Cd, I can write it as m1 into dCl by dm. And if you see, the variation of Cl versus Mach number, also something goes like this. Up to 0.6 it remains almost constant. Then there's a dip. It goes like this. You know, this typically follows Prandtl-Glaudet transformation. And here also you could see, here in this region beyond this transonic, at height up to high subsonic, this slope is positive, dCl by dm is positive, and here dCl by dm is negative. So again, depending upon which flight regime you are flying, the value of dFaz by du1 is also going to change. Right? You could also see that there is an analytical way of handling it using Prandtl-Glaudet transformation. And if you see, Cl is defined as Cl alpha by under root 1 minus m square into alpha and this is at m equal to 0. Incompressible case, this is a compressibility correction. So, and now if we simply take a derivative dCl by dm, you get an expression as m by 1 minus m square into Cl. So analytically also, as a first hand approximation, you can easily find the value of dCl by dm, which will be required in finding the value of CLU. Okay? But for practical purpose, you need to do it in your own way through different testing. And when I am writing dCl by dm, please understand I am talking about, I am conscious about the fact that depending upon the flight regime, these derivatives are going to be different. The sign of the derivatives is going to change. Okay, the final derivative in terms of pitching moment in longitudinal case, which is very, very important derivative. And that expression also will be developing today in this module. Other derivatives will develop in the next module. That in that sense is the final. So it is basically, if I see the pitching moment is written as Qs C bar into Cm, we want to find out dm by du by u1, and which is nothing but Q1s C bar dCm by du by u1 plus Cm SC bar dq bar by du by u1. You have become expert now. You know that I need to develop this at steady state. So that's why 1 I have put here. So I need to put 1 here as well. And also this is at steady state. This is at steady state. Okay? As far as dq bar by du by u1 is concerned, we know that. We have two things to understand: what is Cm1 and what is dCm by du by u1. If we understand that, then our job is done. Here I do further simplification in terms of expression. I write Q SC bar CMU plus CM1 SC bar into rho U1 square, and because I know dq bar by du1 is rho u1 square, and which I can write again as Q1 SC bar CMU plus 2CM1 into SC bar Q1 bar. Same theory, divide and multiply by 2 to incorporate Q1. So I have Q1 SC bar into CMU plus 2CM1. This is nothing but dm by du by u1. Since we are not considering any thrust contribution, the Cm1 is Cm at the, when the aerodynamic moment is 0. Otherwise, for a trim, if thrust is there, then the moment due to thrust plus aerodynamic, the sum should be 0, right? But here, since we are not considering that, so the aerodynamic moment has to be 0. So Cm1 I am putting as 0 at steady state. Cm1 is 0. So I have got this expression as Q1 is C bar CMU. Please understand once I put Cm1 equal to 0, because there are no thrust contribution, because if suppose the thrust line was such that it was also giving a pitch down moment, then to trim the airplane, that pitch down moment and another pitch up moment, total Cm has to be 0, right? The aerodynamic plus moment due to the thrust. But since we are not considering thrust, for trim, total Cm has to be 0 means the aerodynamic moment has to be 0. That is the understanding. Okay? And here it is important to know what is CMU, and let us understand that. dCm by du by u1 is, again I can write it as m1 into dCm by dm. Now focus here. Think of the airplane as the airplane is accelerating towards high speed or supersonic Mach number, what happens? The aerodynamic center of the wing, aerodynamic center of the tail, they move aft. Okay? So if you try to see what is the effect of aerodynamic center moving, of the tail moving aft, that means the tail moment arm is increasing, so there will be a pitch down moment. So dCm by dm will become dCm by dm will become negative. In a sense, it will give a pitch down moment. As I am going to accelerate, it's going nose down, and that phenomena is to be known as tuck under. Accelerating, and this, unless the pilot was aware of this and he puts appropriate elevator correction. So from that point of view, again you see whether you are at a lower subsonic speed or you're going to supersonic speed, you need to be very careful about this derivative dCm by dm, okay, which you can estimate once you know how the aerodynamic center is changing with respect to the Mach number. Okay? So that is also extremely important derivative. But all of this you can estimate either approximately through analytical method, fairly accurately through wind tunnel testing, and more reasonably well through flight testing, or all together in a corroborative manner in an excellent way. All the derivative can be captured within 10 to 15% depending upon what regime you are operating. So today what I try to explain you, how do I find these derivatives which are useful for characterizing dynamic stability through solving the equations of motion, which are perturbed equation of motion, and we try to understand how do I find these derivatives using the geometry of the airplane, using the flight regime of the airplane, whether it's subsonic or supersonic, knowing the characteristic of the airfoil. Once I know these, I know how to model the equation of motion to evaluate whether the airplane is dynamically stable or not. Towards that aim we are inching forward. Thank you very much.